Hi everybody, welcome back to Environmental Organic Chemistry with Dr. Lisa. Today I am going to do some example problems related to vapor pressure. These are example problems. Oops, you're not supposed to see that. These are example problems. This is called Practice Problems Chapter 4 for vapor pressure. This spreadsheet is posted on Sakai, or not Sakai, it's Canvas now. It's posted on Canvas, so you can take a look and follow along. So this first problem is related to Freon 12, which is dichloro-difluoromethane. So the first part of this is problem 4.2 from the textbook, if you care. The first part of this problem is just a really simple PV equals nRT kind of problem. So it's going to be really straightforward. And then later on in this example problem, we're going to take what you thought was so simple about vapor pressure, and we're going to blow it up and make it far more complicated than you ever thought it could be. So let's start with the simple stuff. So, we're an environmental organic chemistry class, and so we're going to give you an environmental problem. So let's say you're out in a dump site and you find an old lecture bottle that's full of this Freon, and of course the Freon is bad stuff. It has to be disposed of properly, carefully. So you want to know how much Freon is in this old lecture bottle, this tank that you found in the dump site, so you know how much it's going to cost you to get rid of it. So the temperature at the dump site is 10 degrees C, because, it's outside, it's cold. The volume of this cylinder, this pressure cylinder, is 3 liters. That's why I call it a lecture bottle, because it's small, and so you use it when you're lecturing, not like those giant gas tanks you see in the hallway. And the pressure reading, because, in this fantasy world, the regulator on the tank is still working just fine, and the pressure on it is 2.7 bar. And so the question is, how much mass of Freon 12 is in this tank? So you're going to use PV equals nRT, and we want to know the mass of the Freon in the tank, so we want to know N, the number of moles. Because if I know the number of moles, I can multiply that by molecular weight, and I can get mass, right? So I'm going to rearrange the PivNert to be N equals PV over RT. So you can look up R. Again, my recommendation is that you look up R in Wikipedia, because there's like every set of units you could ever want. But the set of units that I have memorized from when I was in school is 0.0821 liter atmosphere per mole Kelvin, so that's what I'm going to use here. And if I'm going to do that, I have to convert my 2.7 bar into atmospheres. To do that, I just multiply it by 1.01325. That's the conversion factor to get from bar to atmosphere. So it's not, bars are pretty close. They're within, less than 2% difference between bars and atmospheres. But to be perfect, to be exact, I will convert, to 2 significant digits. You can't tell the difference, but there is a difference here. So 2.7 atmospheres. So here's my pressure, 2.7 atmospheres, times the volume of 3 liters, divided by R and T, which is 10 degrees Celsius, but I have to add 273 to it here to get this in terms of Kelvin units. Expand this a little bit so you can see a little bit better what I'm doing here. Okay, so here's my 273, where I'm adding that onto the temperature to convert it to Kelvin. And when I'm all done with this, I have liter atmosphere per mole Kelvin. I've got atmospheres, I got liters. I converted this to Kelvin. So what I'm left with is moles. So 0.34 moles of gas in the bottle. And I can look up the molecular weight of Freon 12. It's 120.9 grams per mole. Get that from the appendix or from Wikipedia or whatever. Multiply the 0.34 moles times 120.9. You get 42 grams of Freon 12 in this tank. That's your final answer. Yay! And there's much rejoicing. Okay. Now, part 2. This is where it gets a little bit more complicated. You can actually go to some reference books and you can look up the pressure, the vapor pressure of Freon 12 at a variety of different temperatures. Someone took the time, some poor graduate student, I'm sure, was forced to take the time to measure the vapor pressure of Freon 12 at these different temperatures. So what we want to do is we want to graph this data so that we can determine delta H and delta S of vaporization. That's what we're looking for here. And so you hopefully have watched the lectures and you kind of understand how this works, and you know that you don't just plot pressure versus temperature. What you want to do is plot the natural log of the pressure versus 1 over the temperature, right? And if I just calculate 1 over the temperature in degrees Celsius here, I'm going to get some negative numbers, and this is going to be like funky and bizarre. Okay, so sorry, that's my extra one here. And I'm going to get a divide by 0 error because you can't take 1 over 0 and get a meaningful number. So this is your reminder that in fact what you have to do here is convert this temperature to Kelvin. So plus 273.15 to be, very, very exact about it. There you go. And now all of our 1 over t's make sense. And this is the natural log of the pressure. The pressure here is given in kilopascals. So I'm going to multiply it by 1,000 to make sure that I get pascals. There you go. And I have this set up, so now my plot has updated itself automatically. Here's my data, natural log of p versus 1 over t. And you get a straight line. Now notice, just to be clear, if I plot this without doing that weird transformation, I get a curve. These points are curved. If I just do pressure versus temperature, I get a curve, right? So in order to get a line, I have to take ln of pressure and 1 over temperature. Okay, so here's my line, slope, intercept, r squared 0.9999. The graduate student in the lab was doing a good job. That's the kind of r squared you should get when you're doing things under carefully controlled laboratory conditions. We're environmental scientists, so sometimes it works out that way and sometimes not so much. We often get crappy r squareds, but that's life. All right, so a couple different ways we could get the slope. We could just literally read it off the graph, but I'm going to do this in Excel. Slope, y, comma, x, boom, there's my slope, and I can do the same thing here. Intercept, y, comma, x, boom. Okay, so here's my intercept. And so what I know that the slope here, the slope of this line is delta h over r. So to figure out delta h, I have to take the slope and multiply it by r, right? So here's my slope, minus 2439.9. Here's my r. Now notice r has got different units now. Now r is 8.314 joules per mole Kelvin because I want delta H, which needs to have units of like kilojoules per mole. I don't need liter atmosphere per mole Kelvin. This is the frustrating thing about r, right? R's got like 1,000 different types of units. So make sure you're using the right units of r here. So when I multiply one by the other, I get about 20,000. That would be in joules per mole, and if I want to do that in kilojoules per mole, I just divide by 1,000 here, and I get about 20 kilojoules per mole. Now, don't worry too much about the sign, right? The sign is just asking the question, are you vaporizing or are you condensing? It doesn't really matter. It's still 20 kilojoules per mole. It's just a question of the energy going in or coming out of the system. So I wouldn't freak out too much about the sign, but all delta H's really should have a positive value because it takes energy to vaporize things. So let's just put the negative sign in here just to make everybody happy. Now I got a plus sign on my delta H. So the first thing you should always do in my class when you're doing a problem like this is stop and say, does this make any sense? So this is kind of on the low side as delta H vaporization goes, but Freon 12 is a pretty small molecule. It's a methane. It's got some chlorines and some fluorines. Totally, totally nonpolar. So no hydrogen bonding, no polarity, and not a whole lot of van der Waals because it's a small molecule. So it makes sense that it has a small delta H term. Now, in theory, the delta S, and if I could type, this would say delta S, would be equal to the intercept times R, because the intercept would be delta S over R. So to get delta S, you take the intercept and multiply it by R. When I do that, I get 179 joules per mole Kelvin. Again, ask yourself, does this number make any sense? And because you have carefully and diligently watched many hours of my YouTube videos, you know that from Trouton's rule, that dead French guy says that the delta S of vaporization ought to be about 85 to 90 joules per mole Kelvin. So why am I getting 179? Well, it turns out that this baby is wrong. Wrong, 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 okay? And the question is, well, what do we do wrong? Why did we get the wrong number there? The reason we got the wrong number is because we're plotting this in pascals. And so if you converted the units from pascals to atmospheres, right, that would, you'd be multiplying every point here by a constant amount, right? So you'd be moving this up or down, which wouldn't change the slope, but it would change the intercept, right? So how do we convert pascals to atmospheres? Guess what? 101,325 pascals per atmosphere. Sorry, not very good there. But anyway, so what's the natural log of that? Is 11.56. So if I take that and subtract it off of my intercept, actually got it down here, same thing. If I subtract that off of my intercept, now my intercept is only 10. If I had done this in units of atmospheres, my intercept would be 10. And so then if I calculate my my delta S, I would get 83 joules per mole Kelvin. And now all of a sudden, that makes a lot more sense. We said 85 to 90. 83 is pretty close. Now I'm happy. Now my answers make sense. So this is the kind of thing I always encourage you to do. You have to always stop and ask yourself, does this number make any sense? Okay, so this is like the most exact way of determining delta S and delta H, right? Because we have actual data. And whenever you have actual data, you should use it. And that gives you the experimental value of delta H or delta S. And when you have an experimental value, you should always use that. But if you didn't, you could estimate delta S of vaporization from the Kistiakowsky equation. That's a tough thing to say. Try saying it with me. Kistiakowsky's equation says that we need to know the boiling point of our chemical, T sub B. The boiling point is the temperature at which the vapor pressure is 1 atmosphere, right? So we could figure out what the boiling point is from our data up here, right? So 1 atmosphere is about 101 kilopascals. So that means that our boiling point must be below minus 25, somewhere down here, somewhere, because it's, vapor pressure is going down. We need to get it down to 101. So our boiling point must be less than minus 25. And if we figure out what that must be, we do the math here, we get 243 degrees Kelvin, which is minus 30 Celsius, which is indeed a little bit lower than the minus 25 here, so that makes sense. Okay, so we figured out our boiling point here to be 243 degrees Kelvin. We plunk that into the Kistiakowsky equation here, and the Kistiakowsky equation comes back with 82 joules per mole Kelvin, and we got 83 here, and so we're starting to feel a little bit better about everything. Okay, and in the way I have this written, I'm telling you to figure out what's wrong here, but I just told you, so surprise! Okay, now that we have a pretty good idea of what delta S of vaporization is, now we could also do an estimate of delta H of vaporization. Again, this is what we do if we don't have any data. So if we don't have any data, then we say that, again, at the boiling point, delta G is equal to 0. And delta G is delta H of vaporization minus the boiling point times delta S of vaporization. So delta H is equal to the boiling point times delta S. That's what I get here. And voila, this comes out to be really, really close to 20 kilojoules per mole. So hey, it works. Awesome. So Kistiakowsky and Trouton and those guys are not totally out to lunch. It actually works. Now, the other way of getting delta H of vaporization is to use this Gauss-Schwarzenbach equation. Hey, they spent a lot of time on it. You might as well use it and make them feel better. And to do this, your vapor pressure here has to be at 298 degrees Kelvin, which is convenient because, lo and behold, we do have a vapor pressure at 298 degrees Kelvin. In this case, kilopascals, but close enough. We can convert that to pascals quite easily. So in this equation, the vapor pressure must be in pascals at 298 degrees Kelvin. So I can plug those numbers in there. Make this a little bit wider so you can see again. Here's my equation. Minus 8.8 times the log of the vapor pressure in kilopascals times 1,000 to convert it to pascals plus 70. And I get 18.8 kilojoules per mole, which again is pretty close to the 20 that we got from the actual data. So that's telling you this method of estimating delta H of vaporization, it's not perfect, but it's pretty good. So that's 3 different ways of getting delta H of vaporization and in some cases also getting delta S of vaporization for any organic chemical. And in the next video, I'm going to do example problem 4.3, which is similar but with a wrinkle because it's for a different chemical.